Okay, thanks for joining me again. And so to recap, we've looked at where entropy is actually being able to be computed and used for various situations that might indicate that it's helpful to capture some form of model of social behavior. However, lest you think that the problem is already solved and everything is done, I thought it's actually really important to show some of the results here in terms of entropy estimation and the algorithms that we need to use. This actually starts to touch on some fairly complex mathematical issues. I won't go through all of those here. I will touch on a few things and show you a few points that are helpful in our journey. But if anyone would like to follow up and talk to me, find out more about the technical information, please contact me and I'm more than happy to talk it through with you. So really the starting point is to actually think and understand, how do we compute entropy? And in fact, a major limitation of computing entropy is the large amount of data required. So historically, entropy has been used for descriptive statistical purposes, where the aim is to use a very large database, and we estimate entropy then as precisely as possible. So for example, in a typical recent study, 450 million words were used to estimate entropy in English text. So how then can we use entropy in an online analytic sense? The starting point for us was to ask the question, a simple question really, how many samples or pieces of data are actually required to estimate entropy? The interesting thing with this problem is that there have been no previously known solutions. In fact, it's non-trivial. We were able to come up with a solution to this problem, and that was published last year in IEEE Transactions on Information Theory. So I won't take you through all of the technical details, but I will just highlight a few aspects that are actually helpful for further understanding this approach to AI. Now, the finite sample entropy is calculated using this equation as follows. There really isn't any particular assumption given on where those probabilities may lie. In fact, the accuracy with which entropy can be computed is based on the accuracy of estimating those empirical probabilities. What we did was to actually start to look more closely at the model structure, at the distribution of those probabilities. So supposing we've got n0 samples and an alphabet size of m, how then could we estimate what n0 might be? We might think that for many sequences such as language, n0 might be a function of the size of our alphabet. And actually our approach was to consider that in natural sequences such as language, we in fact do know something about the probability distribution. So therefore we can introduce a model of the distribution. And in our case, we did this by applying the Zipf-Mandelbrot-Lie distribution, actually a modified version of that, which is a convenient representation. It's not perfectly accurate, of course, but it actually provides a fairly strong starting point. Now, our approach here is to show that the difference in the closest probabilities is actually a limiting factor in estimating entropy. And we're able to estimate these closest probabilities using this particular distribution and hence obtain an estimate of the number of samples required. To do this, we use the Dvoretsky-Kiefer-Wolfowitz inequality to determine the number of samples required to distinguish between two probabilistic events with some degree of confidence. Now, this is some of the derivation. I'm happy to discuss this in more detail with anyone that is interested. Okay, so to give you a concrete example of how this works and why we find it so interesting, let's look at two cases. So in the first case, what we do is we're wanting to compute the first order entropy of English text. The alphabet size in this case is m equals 26, and we might specify a confidence of, let's say, 95%. In this case, what we find is that the number of samples required is about 10 to the 9. So it's a fairly large number. In the second case, what we did was to consider a much smaller alphabet size of only m equals 5 symbols, and with the same confidence interval of 95%. Now in this case, we find that only around 5,000 samples are required. This is actually very helpful for a couple of reasons, which I'll explain. The first, though, is the fact that there's this interesting relationship between the number of symbols in our alphabet size and the rapid escalation in the number of samples needed to estimate the entropy. So this points us towards this idea of saying maybe smaller alphabet sizes are going to be useful. Okay, so what we see here is actually a way to understand that computing conventional entropy using empirical probability estimation is extraordinarily slow. And in fact, it requires a very large degree, a very large number of samples to get any degree of accuracy. And it's evident that what we really need is an alternative estimation algorithm to estimate entropy in online or real-time applications. So now what we need to consider is a method which we call fast entropy estimation. In fact, I'll take you through the basics of how we came up with this. What we're interested in doing is saying, okay, suppose we've got a very small sample size and a small alphabet. Is it possible to use this type of approach and the knowledge that we have of the distribution involved to obtain a much more efficient estimation algorithm? And in particular, what we've done is to propose that in fact it is possible to use this a priori model of natural sequences and that it improves the performance of entropy estimation. So here we've got a model of a typical distribution of such sequences. How then does this fast entropy estimation algorithm work? So consider a sequence of symbols. We've shown these ones here. And if I asked you what was the most frequent what was the most frequent symbol or the least frequent, you can actually easily do this without having to count them up and give me an exact answer. Just very quickly you can see, and the way that you can see that is actually by computing, or rather I should say estimating the distance between the individual symbols. And so this method is actually based on an approach called coincidence counting. And we've developed this new algorithm for entropy estimation based on this approach. A basic outline of the algorithm is shown here. And in this case, what we can see is a graph that shows the performance of the algorithm. So notice along the x-axis, this is a log scale. And in terms of estimation efficiency, the performance is several orders of magnitude better than conventional empirical probability estimation. And so an example of the use of this algorithm is shown here. So in this case, we have the classic novel Sherlock Holmes, and what we've done is insert short segments of the children's story Dr. Seuss in 3 different parts of the novel. We then compute the fast entropy over short segments of the novel, and then we estimate the entropy throughout. Okay, so what we notice is that the symbolic events used are actually quite arbitrary. In this case, we've chosen a value of m equals 5 using the word lengths. And you can see in this case that the difference in authorship is very quickly determined. Now, it's important to note that this didn't use a pre-trained model. There wasn't any supervision. It didn't use large amounts of a priori data. It really is just a case of simply letting the entropy tell us what it observes directly. Now, in the next example, we created a more sophisticated simulation, and in this case, we used the phonemic structure of speech. So we created a simulation where there are some hesitancies injected into a test section of speech, and it can be clearly seen that the entropy changes significantly when these hesitancies are introduced. So this particular experiment was actually set up as a precursor to determining if it might be possible to detect neurological conditions through analysing the speech of patients that are living with dementia. In those cases, it's known that speech can be affected. So the next topic that we'll talk about is the idea of symbolization. So in the cases that we've discussed so far, entropy is computed using discrete events. And for some systems, there are naturally discrete events. So Joe's diet, for example, uses the discrete pieces of food, and that may work in some situations. But in many cases, we're going to have continuously valued inputs. and therefore it's necessary to provide a symbolization of the input. So for example, in continuous speech, we may have a symbolization that surrounds the length of the pauses within the speech. We could take those pauses and we could construct different classes. For example, we might have 5 to 15 milliseconds, we might have 15 to 25 milliseconds, and so on. So the next idea is actually to say, well, for continuous valued input space, we could actually introduce a more rigorous approach. And in this case, what we've done is create an algorithm which is called CDF-ZML partitioning symbolization. The idea here is that we can actually directly partition the CDF of the input space in accordance with a ZML distribution. So we account for all the data. All that we're doing really is simply performing a classification of the input according to a ZML distribution. And so we see that in each of these successive partitions, there's a progressively larger area under each, and the curve corresponds to the area under the curve corresponds to the most probable event, followed by the second most probable, and down to the least probable. Now, it's interesting to think about this because really it's clear that we could use almost any approach. In fact, there may not be an optimal solution to do this type of partitioning. In other words, it's somewhat arbitrary. And in fact, when you think about it, this starts to then grate against our classical approach, where we are often searching for the most optimal, the most, strategic method of classifying the data according to some strict criteria. Here we're actually starting to introduce this notion that says, well, maybe this is actually not so critical. This is the way we're doing it, and we've done quite a bit of work in this area. We can talk about that offline to anyone that's interested. So in essence, what we're doing is constructing a set of component bases or primitive building blocks with which to compute entropy. And in the next section, I'll show you where this can be taken. Thanks very much.